So here's question 4 from 2019, and this question is concerned with analysing a two-link planar arm using Denavit Hartenberg parameters. And we note that originally it was basically set up in terms of asking you for modified versions of the parameters, but we're going to use the classical ones here. First of all, we see that the arm has two sections. So first link is of length L1 and has an angle associated with it of θ1, and the second link of angle θ2 and a second length of L2 associated with it. There are frames attached just to give you a bit of a hint on how to proceed. Obviously, because this is a revolute joint, the z-axis is going to be the axis of rotation, and the x-axis is, as you can see here, set up to point along the direction of the linkages. That's true for the first case and the second case, and the final coordinate frame is put at the end point of the arm, in the second arm. So what we need to do now is write the table of parameters. And in this kind of arrangement, obviously we've got no twist. So the z-axes are already all pointing in the same direction in the first place. Consequently, the alpha value is going to be 0. So basically then it comes down to how far are we away between the two z-axes of adjacent joints. And from the one at frame 2 to the one at frame 2, we see that's a distance of L1. So that specifies our value of A, and the angle at which we have to account for rotating around the first joint is going to be θ1. So theta is going to be θ1. And also we have a value of D, so there's no offset because it's a planar arm. So that's going to be 0. For the second link, I mean, again, it's just more of the same. In order to get from, if you like, from the second joint to the end point, we have a distance of along the x-axis of L2. So that's going to represent again the A value. Again, there's no shift because it's all in a plane. There's no twist because the z-axes are both aligned, and the angle that we have to account for is θ2, even if it's written in a slightly confusing way on the drawing. So it's asked to calculate what the DH representation is going to be, given the fact that it's a product of two screw displacements, and we're told that this can be represented by a homogeneous equation given as follows. So first of all, we have to account for the rotation around x by alpha, then we have to account for the translation along x by A, then we account for the rotation around z by theta, and then the translation along z by d. So it's asking now, first of all, to write down what these rotation matrices are. ROT, rotation around x, translation along x, rotation around z, translation around z. So let's just, first of all, write down the matrices, and you can look these up from information sheets, of course. I wouldn't expect you to know them off by heart. The rotation around x, we can see that immediately that this is the right one because the x value doesn't change because it's rotating around x, so it's just the y and z components. This is, of course, the homogeneous equation, so the 3 by 3 part is up the top on the left here, and there's no translation associated with it. Translation along x then, by A, in this particular case, is just going to be a shift in x with no shift in y and z. And again, this is a homogeneous transformation matrix, so the 3 by 3 rotation matrix component in this case is the identity matrix. Translation on z then, it's only going to be the z axis which is actually going to be affected, so we have 0, 0 in x and y, and d along the z axis. And a rotation around z is going to leave the z part unaffected, and as we see here, we have the 3 by 3 rotation matrix for z rotation, and in this case again no translation components. So in MATLAB we would write it like this. Of course you can write this as an equation if you're doing it in an exam. Rotation round x multiplied by translation along x multiplied by translation along z multiplied by rotation around z, and that will give us this homogeneous transformation. And in order to get that, we just have to multiply out the matrices we've got at the top here. So if we multiply out the translation along x with the rotation along x, we end up with the term here on the right hand side, and if we multiply the other two out, we end up with the term here on the left hand side. And completely multiplying that out, we get basically the standard equation for what a homogeneous transformation is for a classical link in terms of the angle theta, the angle alpha, and the A and the D terms. So now what we do is we just basically plug into that equation the values for the two entries in the table. So we've got the two rows in the table. First row is basically the theta is theta1 and the A is L1. In the second row we have theta equals theta2 and A is L2. Alpha is always 0 and D is always 0. So we just have to plug those values in. I'm just showing you what it looks like if you did it in MATLAB, just to make sure I don't make any mistakes. And they're basically identical, except you've got a theta1 here, and you've got a theta2 here, you've got an L1 here, and an L2 here. And then what you do is write basically the transformation for getting back from the endpoint all the way to the base frame. So basically you have to do the transformation from frame 2 to 1, and then from frame 1 to 0. So it's basically multiplying out those two matrices that we just had. Again, it becomes incredibly tedious to do these things by hand, so you weren't actually being asked to do that. This is kind of where you'd have to get to in order to get the marks in this kind of question. But obviously if you've got MATLAB available, you might as well use it. This is just fully multiplying it out without doing any simplifying. And if you use the simplify command, it will do some nice simplifications for you, and you should immediately recognize some of this as being the endpoint of a two-link arm in terms of second link length, cosine and the sine of both of the angles added, and then first link length multiplied by the cosine of just the first angle.